Okay, well, welcome everybody to today's SoFiE Seminar. I'm Andrew Patton. Today, I'm very happy to have Patrick Gagliardini from the University of Lugano as our presenter. He'll be talking about extracting statistical factors when betas are time varying. His discussant is Seth Pruitt from Arizona State University. We'll be following the usual format for the seminar. We'll have 40 minutes for the speaker, 10 for the discussant, and 10 for questions from the audience. If you have a question during the talk, you can use the raise your hand button down at the bottom of your screen, or you can use the Q&A button to ask your question. And then maybe once or twice during Patrick's presentation, he'll pause for questions and I'll unmute you and get you to ask your question directly. Or you can wait and save it for the last 10 minutes, but please feel free to ask as the seminar progresses. So now we'll start the presentation. Patrick, if you'd like to share your screen, you can begin.
Can you see my screen?
Yes.
Okay, so good afternoon or good morning, everybody, and thank you, first of all, for the nice invitation and this opportunity. So this is joint work with Alma, who is a PhD student at the Università della Svizzera italiana in Lugano. And that's a work about extracting latent factors from high-dimensional panels with conditioning information. Okay, so after a short introduction, I will present the methodology in this paper, so the model and how do we identify the parameters and the way we estimate non-parametrically these parameters. And then I will present the results in our empirical analysis. So this is a work in a line of research, extracting latent factors from high-dimensional panels of equity returns to span pervasive risk, estimate equity risk premia, or estimate the stochastic discount factors and other applications, where the latent factors are used instead of selecting from a zoo of observable factors. Now, when using this individual stocks, it's very important to accommodate the time variation in the betas of the stocks and time variation of the premium. And there can be systematic components in the time variation of the betas. It could be that some factors actually become more important or less important in some phases of the market, and maybe the numbers of these factors is also time changing. So this leads us to consider a problem in which in our high-dimensional factor models, the betas change over time. Maybe the number of the factors is also changing across time, and we would like to have something like a dynamic version of principal component analysis to make inference on the factor space. So on the methodological side, the contribution of this paper is to introduce a novel approach to extract factors in the presence of conditional information using instrumental variables. And our approach is pretty general, rather almost model-free regarding the dynamics of the beta, and we allow for the betas of the assets to be function of a large number of variables in our conditioning information. And actually, the idea is to use some machine learning techniques to accommodate this high-dimensional conditioning information. So in this way, we can estimate parameters like the path across time of these latent conditional factors or conditional canonical correlations between these latent factors and some observable factors, for instance. Now, when we come to statistical inference, we are going to use the so-called double machine learning, which is going to allow for some asymptotic normality results and confidence interval construction for parameters which are low dimensional features of this latent factor space. something like, for instance, the average value across time of a conditional canonical correlation. I will come back to this later. In terms of the empirical contribution, in this paper, we conduct an empirical analysis. We apply this methodology on a panel of individual stock returns, US stock returns. And briefly, some of the findings are that we do have a dominant factor, a dominant conditional factor in this panel, which sometimes or most of the time accounts for almost 50% of the variability in the panel, in some sense that I will explain later, and sometimes more than that. We have some evidence that we need perhaps 3 or 4 conditional factors to exhaust the purposes risk, maybe sometimes less than this in some phases of the market. Indeed, we have some evidence of the time variation for these numbers of conditional factors. When we focus on the first conditional factor, so let's say the dominant one, we find that this factor, not so surprisingly, correlates most with market, on average about 60%, but in a time varying way. And in some phases of the market, other factors correlate more with this dominant factor. And finally, one dimension in the conditional factor space is found to be rather well spanned by, let's say, Fama-French returns, but other dimensions are not well spanned by Fama-French returns. So in our work, we build on large literatures where the time varying betas apply to observable factors, for instance, or the latent factors have time variation in their betas. The literature where both we have latent factors and time variation of the betas is smaller and more recent. There is an important contribution on instrumental principal component analysis by my discussant Seth, and there are other contributions, some of them I'm mentioning here. In the paper I'm presenting today, our focus is more on the conditional factor space, on conducting the inference on this conditional factor space by being rather agnostic in some sense on the dynamics driving this beta. And we allow for the fact that the conditional factor space, the conditioning information set, driving this factor space is rather high dimensional. And we would like to see how the use of machine learning techniques can provide advantages or disadvantages in the inference on this conditioning factor space. And so we focus a lot on allowing for this high dimensionality on the variables which are driving this conditioning set. And so on this focus, we rely on a long list of other papers. I apologize if not all of them are cited here, which are exploring the use of machine learning in finance. Okay, so let me move on. So in this part, I would like to present the methodology for this paper. So we consider a model defined here in this equation where it's a conditional linear factor model. The y's are the exact returns of the assets, let's say, and on the right-hand side, this vector ft is a vector of unobservable factors. And as you see, the intercepts and the loadings of this in this model are potentially time varying as a function of some information set, which is not specified at the moment. Now, if we think that these assets are drawn from an underlying continuous populations of assets, as we did in previous work, then by assuming that there are no asymptotic arbitrage opportunities, there is a restrictions relating the intercepts and the loadings, and if you impose this restriction here, you get this equation here, number 3, where the vector GT is basically a shift of the vector of the latent factors such that the conditional expectation is equal to the risk premium. Okay, so that's the equation basically we start on, and the first problem is about how do we identify this the parameters or various features in this model, where the complication comes from the fact that these loadings are time varying as well. Okay, but in a predetermined way. And so for the identifications of these parameters, we are going to use an instrumental variable method. So imagine you take one date. So if you take one date here, and you consider your vector GT as a vector of your unknown parameters you want to estimate in the cross section, and building on some previous work with my co-author Christian Guerrero, we consider as instrumental variables as a vector of variables which are, variables which are cross-sectionally uncorrelated with the error terms, but full rank correlated with the betas, with the unobservable betas, okay? So I will denote by this gamma T-1, this cross-sectional cross moments between the instruments and the loadings. So as you see, potentially this matrix gamma is time varying, is function of some information, and this information, which are denoted by this calligraphic FT, intuitively is the information which is spanned by the cross-sectional averages of quantities. So something like a sigma field of non-diversifiable shocks. So the shocks that remains in a large cross-sectional averages. Okay. Now, we can use this instrument variables to construct returns of instrument-weighted portfolios. So these are these XITs. So portfolio returns, in a large portfolio returns weighted by these instruments, and plugging the model and using the properties of the instruments, the part with the errors cancels in the limit, and this part basically obtain that this portfolio or instrument weighted returns are nothing but a transformation, a conditional transformation of the vector of the latent factor. Conditional because it can depend on time t information. Now, if I freeze the conditional information that I have on time t, so if I condition on this information set of the shocks, which are non-diversifiable, and I compute the conditional variance of this vector psi t, I immediately recognize that this conditional variance as a rank k, where k is the number of the factors. So this matrix of the conditional variance of the portfolio returns will be reduced rank if I have more instruments, as I'm assuming more instruments than factors. And the rank of this variance covariance matrix is exactly the dimension of the factor space, which is identified in this way. And moreover, I noticed that my matrix gamma t minus 1, or the columns of this matrix gamma t minus 1 are spanned by the eigenvectors of this conditional variance matrix associated to the non-zero eigenvalues. Now, given that the factors are unobservables, they're always defined up to some rotation. And in this conditional setting, I can rotate this factor conditionally, so as a function of time. And I can pick a rotation that is useful for the purpose of identification. So I can choose one normalization of the factor of the latent factors, such that this gamma matrix, this cross moments between the loadings and the instruments, exactly coincides with this matrix of eigenvectors that I have denoted by this JT minus 1. Okay, so for some part of the paper, I'm using this normalization assumption in which this cross moment matrix gamma actually coincides with the matrix of the eigenvectors associated to the non-zero eigenvalues of the conditional variance matrix of this instrument-weighted portfolio returns, which I can always achieve by a rotation of the factors. Now, if I have that gamma t minus 1 is equal to jt minus 1, then if I go back to this equation and gamma t minus 1 is jt minus 1, I can easily solve this equation for gt by multiplying both sides by the transpose of my matrix gt minus 1, and I get this. And you might recognize that actually in this way, my vector of latent factors turns out to be nothing else than essentially the conditional principal components vector of the instrument weighted return. So in some sense, if I might try an analogy with the instrumental variable method, so in this equation, we consider the g for a given time t as the vector of the parameters. The problem is that the regressors, the b, are unobserved, but we are using a set of instruments, and for computing the instrumental variable estimator, it's not necessary that the matrix X, let's say, of the regressors is observed, but what we need is that the cross product Z times X, so the matrix of the instrument times the matrix of the regressor is observed. And by means of this normalization, I exactly achieve that I can have this matrix of the cross terms between the loadings and the instruments is actually corresponding to some feature that I can identify from the conditional variance of the portfolio weighted returns. Now, if I normalize my vectors of factors to be zero mean, I can simply then recenter conditionally the previous expression and get this expression for the factor. So this is basically a way to identify one rotation in the conditional factor space, which corresponds to conditional principal components of this vector of instrument weighted returns and the associated vector of risk premium. And this rotation of the factor space is identified from some feature of the conditional variance of the xi, basically these eigenvectors. I can have a different perspective on this if I consider, let's say, if I consider having a vector of observable factors, let's say, so let ft with this upper index O denote a vector of observed factors. And let's assume that, or we would like to understand what, to which extent this latent factor space and the space of the observed factors overlap. So for this, we can consider the conditional canonical correlations between these two vectors, which are basically the square roots of the eigenvalues of this matrix, which is written here, Now, if I plug in for my latent factor ft, the previous formula, I recognize that this matrix turns out to be this expression in red, which basically means that I can identify this conditional canonical correlations between the latent factors and the observed factors, basically from the conditional second moment of the vector of the portfolio or instrument weighted return, let's say, augmented by the vector of the observable factor ft, okay? And so this makes this conditional canonical correlations identifiable if I identify this conditional second moment of the portfolio returns and the observable returns. And by means of this conditional canonical correlation exercise, I get not only conditional canonical correlations, but also conditional canonical directions. And so I can define another rotation in the factor space of the latent factor space, which corresponds actually to the directions in this latent factor space, which are the most correlated with some vector of observed factors. And it turns out that they have an expression like this, which is very similar to the previous one, but here the Vt minus 1 is a matrix of eigenvectors, not of the conditional covariance of psi t, but of this matrix obtained from conditional canonical correlation. So this gives a different normalization, or the identification of a different rotation in the latent factor space, not related to principal component, but rather to canonical correlation. Now, to conclude this part on identification, so what's the general form of the parameter of interest? Well, to be concrete, let us assume that this sigma field of non-diversifiable shock is generated by a Markovian vector of observed variables, this Zt, which can be a realistic assumption if I allow this dimension d to be rather large, okay? Well, then all the parameters I've shown before, the parameters of interest shown before, so let's say the latent factor space identification or the conditional canonical correlations, basically admit a form like this one. So they can be written as some known function, let's say phi, of this functional parameter theta 0, which corresponds to the conditional expectation given Zt minus 1 of a vector whose elements are the elements or the cross products between these instrument weighted portfolio returns psi t, or augmented by this, possibly augmented by this latent factor, okay? And so in this setting where the dimension d is large, so the hard problem is exactly, so the difficult problem is exactly to make inference on this I-dimensional parameter. So in terms of estimation now, so we follow an analogy principle. So first of all, we make this portfolio return psi t observed by the cross-sectional weighted averages of the asset returns with the instruments. And then we estimate this functional parameter by a high dimensional non-parametric regression in time series. And given the dimensionality of Zt minus 1, which can be large, we consider methods like artificial neural networks or lasso and post-lasso methods, for instance. And then the non-parametric estimator for these parameters of interest has basically this expression. Now, by building on some available results in the literature, when both dimensions of the panels are large, we can get some results about we can establish results about the convergence rates of these parameters. but the results, for instance, for pointwise inference, so for inference on a given time point, are much more scarce to our knowledge. So actually, for having some inference, we follow a semi-parametric approach, and we focus on some finite dimensional feature of this high dimensional or infinite dimensional parameter. So something like the parameter C in this equation being the expected value of the feature of interest. So for instance, if the feature of interest, the gamma T is a conditional canonical correlation, here I'm speaking about making the inference on its expected value. You consider parameters more general than that, but for instance, the expected value. Now, in order to accommodate the high dimension of this parameter theta, we use the so-called double machine learning approach, which basically consists in using a locally robustified version of the moment condition identifying the parameter C. So in this equation, if you cancel this red part, you recognize this is the moment equation defining this parameter. Now this equation is augmented by means of this term, which involves something like a Gateau derivative of the parameter of interest with respect to the functional parameter theta. And by means of this augmentation, while keeping the fact that this moment restriction is still valid, so it is equal to 0 at the true parameter value, actually by subtracting this term with the first order derivative, we achieve the fact that the first order derivative of this term with respect to the parameter theta is actually equal to 0. So we get something like the fact that the moment function is not sensitive, at least at first order, to changes in this infinite dimensional parameter theta. And so then the idea of the double machine learning estimator is basically to compute an average across the sample by augmenting the estimate by means of this part, and also using sample splitting technique in which basically you are constructing the average on a different sample compared to the sample that you're using to estimate your theta parameter in order to kill some terms, which are low convergence rates. And under some conditions, you can show that the estimator of this parameter, of this low dimensional feature is asymptotically normal under some conditions. And here I'm referring to the papers in the literature considering this type of results mostly in an IDE framework, and in the paper we extend this in a time series framework. Okay, let me move now to the last part of my presentation, where I would like to talk about some results of our empirical analysis. This empirical analysis is still in progress, so comments are, very much welcome. So we apply this methodology on large panels of US stock returns, monthly returns on individual stocks. So the cross-sectional sample size varies in the samples between 2,000 and 9,000 stocks. We use as instruments, or we borrow our instruments from the previous literature, building up a vector of this instrument-weighted portfolio returns of dimension 22. And we also borrow some variables for generating this set of the information set of the non-diversifiable shock from the literature, which in our application is 19 dimension. Now, we start with the question about the numbers of factors, of conditional factors. Now, I've not presented this so far. So in the paper, we show that one way to approach the problem is to use ratios between consecutive eigenvalues an estimator of the conditional variance covariance matrix of this portfolio return. So the idea is reminiscent to the eigenvalue ratio criterion. So you pick the numbers of eigenvalue when you see a big drop in these eigenvalues. And we show that in theory, this provides a consistent estimation method for the numbers of conditional eigenvalues. Now, in this plot, what I display are the time series with 6 months average of the different eigenvalues ratios. So the blue line is the ratio between the first and the second eigenvalue. Then the orange is second to the third, etc. We see that basically across the sample, most dates, the first eigenvalue ratio is the largest, which according to this criteria is suggesting one conditional factor. So actually we interpret this as an evidence of the presence of one dominant factor in this data set, which is a finding of course here. So the vertical gray areas in these pictures are NBOR recessions plus some financial crisis. So to understand more about the role of this dominant factor, and also to understand whether, so what's the role of possibly other conditional factors, we are using this argument. So if we go back to this assumption, this normalization of the latent factor space I provided to you in assumption 2, it turns out that it implies that the factors are conditionally orthogonal, and the conditional variances of these factors actually corresponds to the ranked eigenvalues of this conditional variance covariance of the portfolio returns, which basically means that we can write the trace of these conditional variance covariance matrix as a sum of the contribution of the different eigenvalues. So in this way, we can define ratios like this one, in which we compute the percentage of the total variation in, or the conditional variation in these portfolio returns, which are explained, let's say, by the first R factors, by summing up these eigenvalues up to number R. So in this picture, this is a time series for these, we call an accumulative explanatory power ratio. So the blue line is when you consider the first factor, the orange when you consider the first 2 factors, and then 3 factors and 4 factors. And so as you see from the blue line, it seems like according to this metric, for most states, the first factor accounts for almost 50% or close to 50% in this total variation. There are phases in which this percentage is going up maybe to 70 or 80%. And so this is, again, a manifestation of the fact that this factor is dominant, but you see that the contribution of the other factors is not negligible, and maybe to exhaust completely the factor space, we maybe need 3 or 4 factors. Certainly there are phases like this one in which it seems like that even with 2, 3, or perhaps 2 factors, we exhaust a rather large percentage in the total variation. So again, drawing confidence bands point-wise across this bands, we are not doing this at the moment, so it's probably rather difficult. But in principle, we could use the double machine learning methodology I've mentioned to you, for instance, to estimate an average value of these lines and construct confidence bands across them. Now, let's imagine we just focus on the first and the dominant factor. So here, considering this first latent factor, this principal component factor, so the one with the highest variation explained in terms of this conditional principal components. Here I'm displaying the conditional canonical correlation with market. So market is the factor having, on average, the largest conditional canonical correlation with this principal component factor. In some periods, this conditional canonical correlation is maybe close to 80 or 90%. In other periods, that's low. So you see that there is some evidence about the fact that this first conditional principal component factors has some time variation in the correlation with the association with the market factor. And we can consider also the conditional canonical correlation with other observed factors. Here, for instance, the orange line is conditional canonical correlation with high minus low. And this seems pretty large in some periods larger than with the market. So according to this evidence, the dominating factors as time varying composition in terms of its association to Fama-French returns. So in this picture, we compute the conditional canonical correlation when we take three latent factors, so F1, 2, and 3. And we compute the conditional canonical correlation with the three Fama-French factors, okay? And you get and I display the time series of the three conditional canonical correlations, again, with 6 months average. So we can observe that the first one is rather large. So again, we could use, this is not yet done, we could use double machine learning to compute, to estimate and to give a confidence interval for the average value of them. But in this picture, I just observed that the first conditional canonical correlation is rather large, suggesting that there is one rotation in the latent factor space, which is, according to these numbers, pretty high, well explained by some combinations of the Fama-French factors. The other two conditional canonical correlations seem smaller, suggesting that other directions in the conditional factor space are not so well spanned by the Fama-French factors. Okay, so these conditional canonical correlations are useful to make. In this case, they suggest that to some extent, there is a superposition of this conditional latent factor space with observable factors, but in other direction, this superposition is weaker. Okay. So maybe in the interest of time, I think I will skip this slide and jump to the conclusions. Basically, to summarize, in this paper, we provide one possible dynamic version of the principal component method to extract latent factors from a high dimensional panel with conditioning information. And we take advantage from instrumental variables, and we allow for a high dimensional set of conditioning variables driving the time variations of the betas and the mispremia. We do find some evidence on the fact that there is a time variation about the importance of the factors in this latent space. We find one dominant factor and maybe 3 or 4 factors necessary to exhaust the pervasive latent space. In terms of the inference, we take advantage of this double machine learning in order to make inference and construct confidence intervals for low dimensional features of this object, like expectation of conditional canonical correlations, or more general parameters. They could be covariances, for instance, between the conditional canonical correlations and some variables, if you want to see how the conditional canonical correlation moves in terms of some variables. And we find some evidence on the fact that maybe one direction in this latent space is rather well explained or spanned by the found French factors, maybe not others. But as I say, the empirical result is a preliminary. We are working on this, and there are other dimensions that we plan to investigate in this paper and others, and I look forward to your comments. Thank you very much.
Okay, thanks very much, Patrick. That was great. We have a question from the audience, but I think given we're right on time with the presentation, I'll turn to the discussant, Seth Pruitt, and then we'll come back and open up for questions from the audience.
Okay, great. You can hear me, Andrew?
Yes.
Okay, great. All right, thank you very much for inviting me to discuss this interesting paper. I really enjoyed Patrick's presentation of it. I'm just going to walk through what I understood about the procedure. That's basically what I do, is try to simplify things down for myself because I need them simple. So the overview here, estimated conditional factor model using instrumental information, allowing the loadings to have a very general shape that is in a particular way related to the instruments. We'll come back to that. And allowing the factor space to vary. Okay, so these are the important features of what's going on here. And really 3 and 4, I think, seem like the real like cutting edge thing that this paper is doing. Okay, so how does this work? Okay, here's a conditional factor model I've just written down. This G object has 2 pieces. The risk premium is related to whatever is the conditional expectation of this factor F in this new idea, new being the Greek letter. Some key ideas here. This E of C is going to be a cross-sectional average, just what Patrick described. And here's like the important way in which the instruments and the loadings are related. As he described, there is a full rank matrix. The rank is little kt. That relates the instruments W to these loadings, which have a very general shape, perhaps. And then we have this identity that comes, not identity, but an equation that follows this C turns out to be this, in essence, like instrumental variable projection matrix, gamma times G. And an important aspect of that result right here then would be that if we ask what is the conditional variance of this C object, well, it would be this gamma matrix sandwiching the covariance, the conditional covariance of this G object. And we care about that because G is encoding the factors that we care about, the factor space that we care about. Okay, so there are a few ingredients that we need. We need to form a C, right? Those are managed portfolios. So that's okay. We have many ways that we could manage those portfolios on the basis of different firm level or stock level information. So that's how you obtain those. One needs a normalization assumption, as one almost always does in latent factor models. And the particular one here is going to be that this gamma, this kind of instrumental variable projection matrix that has little kt columns, we're going to take those columns to be the eigenvectors of this conditional covariance matrix that we can estimate at each point in time. Because we take gamma to be that, then G will be these eigenvectors. Most of the time it's 1. There might be 2 or 3 times this C object, the managed portfolios. Okay, just recall that's what G is. And now we make another kind of normalization assumption here. We assume that the conditional mean of the factor is 0. That's going to allow us to obtain F from this decomposition here. Now, in order to get anywhere, this model is making these normalization assumptions, which you always have to do. And it's also assuming no arbitrage here to get its estimates. I will note, my work with Brian and Yanan does this too, essentially by saying that this new object is 0, and it's justified because we're not taking a stand on like a dynamic price of risk or using that kind of thing to estimate the factors, and in the end they're tradable. So that is something that we can impose in our model as well and actually test, which I think is interesting. So these are the 2 main ingredients you've got to get to make this procedure work. You've got to get the conditional expectation of these portfolio returns, and you've got to get little k, okay, the dimension of that instrumental variance kind of projection thing, that gamma matrix. How many columns does it have? Okay, so what they take this to be, this conditional expectation, is a function of aggregate info, right? And they're going to allow this function of aggregate info to be pretty general. They're going to estimate it from a feed-forward neural network with a single hidden layer. They also discuss this other method. Now, so then it matters what you're going to include as the information. They're going to include in the aggregate information Goyle-Welch predictors, Fama-French factors, and macro aggregates and past portfolio values. I presume these up here are lagged. And then the managed portfolios are going to be ones that they can construct from the individual stocks themselves using the characteristics that Freiberger et al. Had and that we used. And they're also going to add some portfolio returns just directly. Okay, so that's going to be the space of managed portfolios and the aggregate information they're going to use to get this conditional expectation that they need for the procedure to work. And then this little k, the rank of the covariance matrix, they're going to, as Patrick very clearly described, they're going to be essentially looking at my colleague Min's estimator that looks at the slope of the scree plot, the eigenvalue kind of scree plot, to see, okay, where are the significant eigenvalues based on the slope of that scree plot. Okay, so a few comments that I have on this. The results are suggesting that KT equals 1 most of the time. That is, there's one factor. So this is an interesting result, and I just would love some more intuition about what's going on here. So imagine, you know, this C, the managed portfolios, includes the Fama-French 5 factor model plus momentum, all right? So consider either the factors themselves, or go ahead and try to get out the predictable component and just look at like VAR1 residuals. If I was just looking at these 6 portfolios, and I looked at the eigenvalue ratio maximum here, you can see that over time, I would be picking up that kind of conditionally, in this rolling window sense, conditionally, the residuals from a VAR, just the factors themselves over the last 5 years, would suggest that there are, well, it's bouncing around, but between like 3 and 4 a lot of the time factors. Now, if instead I add to it all the managed portfolios that Brian and Yanan and I had, then at this point, now I see that the dominant eigenvalue tends to be that 1. So I see evidence of that. It's just interesting here how the dimension, how many portfolios in C matters here for the result. So that's one thing that I just noted. 2, what do the loadings look like? This is essentially Frank's question that he put in the chat. And I believe that right here, these aren't really discussed in the paper. I don't know if they're estimable. They're allowing these loadings to take a very general shape, and then just estimating how the instrumental variables are related to that space, basically. So that induces a lot of generality, but I'm not sure about the interpretability. I think that that takes a hit a little bit, the generality. And so I'm not sure exactly how Frank's question could be answered here. If you have a simpler model, for instance, the one that Brian and Yanan and I wrote down, it's very easy. You include that network centrality measure as one of your instruments, and you see what the linear function that you're estimating looks like in it. So there's a trade-off there. There always are, right? This paper is work in progress. And so I would just suggest that they pursue pricing results. We are interested beyond like the dimensionality of the factor space. We'd like to know about pricing assets. And so you could think about pursuing results just on R-squareds, which are still kind of statistical objects, but also Sharpe ratios. This is going to help us clarify what exactly this added technology is buying. There's a lot of added technology in this procedure. Maybe it is worth the cost of bringing this added technology, but I believe pricing results would really help motivate that. And to my earlier point, it's kind of unclear how to go back to individual stocks here. And so I'm not sure exactly what those results will turn out to be, but they might be quite good. Recommend pursuing that. Finally, I think you addressed this. In the interest of time, I have one other small comment. I'll just leave that for Patrick. Let me just wrap up What did this paper do? It estimated a conditional factor model. It used instrumental information, which is now being recognized, you know, as an important, it's basically just conditioning some moment equations, right? It allows the loadings to have very general dynamics and the factor space dimension to vary over time. And those are great general directions. It does cost a little bit in terms of interpretation, I think. And I'm looking forward to future drafts of the paper that have more empirical punchlines. Thank you.
Okay, well, thanks very much, Seth. That was great. Patrick, maybe if you would like to respond, you can go ahead, and then we've got a couple questions from the audience.
Yeah, thank you. First of all, I would like to thank Seth for this very, very useful discussion. So he made very fair points and useful, or maybe I can address some of them. So the numbers of factor k equal to 1. So indeed, in the earlier versions of the paper, we were putting maybe some more emphasis on this interpretation of one conditional factor. Now we realize that actually this selection of k equal to 1 in most dates has to better be interpreted as the fact that there is one dominant factor in the paper, but this is not the only factor which is there. And I think indeed, so the result of Seth is probably showing also the fact that when we have these additional ones, you go back to k equal to 1, probably because you find that one of these factors is clearly the dominant one. So I think that this is an effect of the difference between the fact that there is one dominant factor, but not only one factor in this panel. Estimable betas, yes. So it's not the focus probably in this paper or in the version of the paper. We could estimate the betas once we had an estimate of the factor. So once you have estimated one directions of the factor, you could estimate the betas by some non-parametric regression. So in this case, you have to take a stance on what's the information set that drives the loadings, perhaps again on high dimension, but okay, this is maybe for another paper. So here we are focusing more on aggregate things. So maybe what we would like to see are more features, not of the specific betas of some assets, but maybe how do some features of the cross-sectional distribution of the betas do change across time, for instance. So again, an aggregate and not the single stock betas, but just the focus of this paper compared to others. And maybe I conclude on pricing results. Yes, definitely. So in some part of the paper, I've not shown here. So we deduced what is the stochastic discount factor implied by this model, by this linear model. It can be written again in this form of the parameters of interest I've been mentioning in my presentation. So in principle, the SDF can be estimated in the same way, and features of the distribution of the SDF, but it's an open question, of course, to see how do the pricing of so what's the pricing of these factors, how these factors would they improve the pricing, or another question we are not addressing at the moment is, for instance, the risk premium of these factors. So I agree that there are plenty of directions in which we could improve the empirical path. Maybe stopping here and thank again Seth for his discussion. Thank you.
All right, well, great. Well, Seth mentioned there was a question in the chat box, but I think only the panelists get to see it. So maybe, Frank, I'll unmute you, and if you'd like to ask it in person, you can go ahead.
Oh, okay. Can you hear me okay?
Yes.
Yeah, well, maybe I'll just read it or something like that, but just to make sure I don't forget anything exact. But, you know, Camille Yilmaz and I have proposed measuring time, what we call, you know, network connectedness, in particular time varying network connectedness via network centrality measures like in degrees, out degrees, mean degree, and so on, that we get off of, or get from a time varying regularized, if necessary, if it's high dimensions, vector autoregression. So, you know, that's sort of our take on it, but there's no factor structure that we're assuming or splitting. So the question then is, if there is factor structure, an obvious and natural way to think about connectedness, of course, would be some aspect of the loadings and size of the loadings in particular, and time varying connectedness would, of course, be time varying loadings. So the question was just whether you have any results along those lines, or know of anyone else's results that sort of relate aspects of time varying network centrality to time varying latent factor loadings in environments that have factor structure.
Can I answer now, or Andrew?
Yes, please go ahead.
Okay. Well, thank you, Frank, for this very challenging question. No, actually, we do not have in this paper results along this. I've seen, you probably also know some research in which you estimate models which have this var structure in high dimension plus unobserved factors. So you combine the autoregressive part and the var part, but with stable loadings. So I agree it would be interesting to extend with time variations of the loading, but this is certainly beyond what we can do at the moment with this paper. But it would be, for instance, yeah, I agree with you that one can search in this direction to maybe to have interpretation for the factors that we extract.
Thank you.
In order to just completely self-promote, Frank, you could talk to us and we could estimate that in our simpler model.
I'm sorry, say that again, Seth?
We could estimate what you're after in our simpler model if you want to talk about that offline.
Oh, sure. Yeah, sounds good.
It's self-promotion by discussants. This is a time-honored tradition, so that's permitted. We have one other question. Marcus Pelger has a question. Marcus.
Hello, can you hear me?
Yes.
Thank you very much for the presentation. Very nice. I have just one comment about the number of factors. So this eigenvalue ratio criteria, by looking at the maximum eigenvalue ratio, as you pointed out, is sensitive to a dominant factor. So Natsky provided another estimator looking at when do you have a small difference between eigenvalues. And I also build on his work saying, well, let's look at a clustering argument and eigenvalue ratios. So that is based on roughly the same statistical assumptions, but is more robust in the presence of dominant factors. So I propose you could do the same and look at eigenvalue ratios and see when they start clustering. And that would be the beginning of the idiosyncratic spectrum. And that would probably provide more evidence towards a 3 or 4 factor model.
Yeah, that's a very useful. I remember you gave me this command. I would love to go in this direction. So we tried at the beginning. So it has to be emphasized that to get some inference method in this framework, that's not exactly the framework in which this methodologies like eigenvalue ratios or other criteria are used typically, in the sense that in the standard setting, you are computing these eigenvalues as the eigenvalues of a high dimensional variance covariance matrix statically, while here are the eigenvalues of a conditional variance in a low dimensional setting, but in which the conditioning information set is very high dimensional. So this changes quite a lot the statistical properties of these objects. So in particular, understanding the statistical properties of the eigenvalues of these estimated conditional variance covariance matrix is completely different. So that was creating some difficulties to us to expand on those directions, but we will give more effort and more energy to try to see whether these alternative approaches could work. So we were able to make the eigenvalue ratio work from the theoretical point of view, but we know that, okay, there is this dominant eigenvalue ratio. That we will certainly try again with this clustering method, whether we can try to make it work in this framework, which is not the standard one.
I mean, just to point out, I'm aware that the assumptions that you use for clustering arguments are typically strong based on random matrix theory, and that wouldn't work in your setup. But there's a trick around that by using a perturbed eigenvalue ratio test statistic that is only based on rate conditions. And I think that's what you are using here as well. I mean, I would assume you only derive certain rate conditions.
It is.
And that is how you motivate the largest eigenvalue ratio.
Yes.
And the same assumptions are sufficient for a perturbed eigenvalue ratio for clustering. So that's in some of my papers. You can have a look at that.
Okay, so that's very good news. Fantastic. Okay.
All right, great. Well, this seems like a good time to end it. So let me thank our speaker, Patrick Gagliardini, and Discussant Seth Pruitt for an interesting hour of talks. This was great. And before we leave, let me do a brief advertisement for the next SoFiE seminar. So the next SoFiE seminar will be in 2 weeks' time. The speaker will be Lars Peter Hansen from the University of Chicago. Lars is the 2013 Nobel Prize winner. So we're in Nobel season right now, and it's good timing to have him come and present. His discussant will be Noor Madahi from the Toulouse School of Economics. So please join us in a couple of weeks' time.